phagocytosis. Now remember, macrophages love to eat almost anything, but it really loves bacteria and viruses coated with antibodies. It's like putting chocolate over steak or something. Okay. But especially if you found out neutrophils are extremely picky at what they eat, but if you cover it with antibodies, it will phagocytize it. It actually enhances phagocytosis. So one way is, it's called, do I have a picture of it? No, I guess I don't. Receptor-mediated phagocytosis, where it has receptors on the cell membrane, and if the antibody with the bacteria binds to that, then it actually stimulates the phagocytosis. So it's not just normal phagocytosis, but you actually have more phagocytosis as a result of it. So that's one way in which we can enhance phagocytosis. Another way is you can mate them together and phagocytize it. So think of it this way. Think of phagocytosis as like when I pick up Legos pieces for my kids when they're young. When they're like 1 or 2 years old, my kids love to play Legos. So I come home and you know what? It's all strewn throughout the living room, dining room, kitchen, even my office. I have to pick them up one at a time. But when they were 5 or 6, when I come home, they're still playing with Legos, but now they're in the form of houses, buildings. So I just grab one building and I can put away 50 Lego pieces at one time. And grab another one, 25 goes. Same thing here, instead of phagocytizing one virus, one bacteria, you phagocytize 50 at one time. So that really enhances the speed at which you can undergo phagocytosis. So not only do we have enhancing the phagocytosis because of the antibody, when the antibody binds to the antigen, it's called antibody-antigen complex. That causes this special type of phagocytosis, but also you tend to phagocytize many at the same time. So neutralization of the pathogen, enhanced phagocytosis, and the third is what we call the complement reaction. This is where we get a mixture of adaptive and innate immunity, because complement is actually considered innate immunity because it will destroy any cell. But the problem is we don't want to destroy any cell, including your own cells. We only want to destroy cells that are foreign. And the way we do that is we need to make it specific so that it turns out complement will not be activated unless you have antibodies on that cell that's bound to that cell. So let's see. I have a picture. Okay. This shows it here. So this is showing the cell membrane, and when antibodies bind to it, these are complement protein that's part of the protein in your blood plasma. So when the complement protein encounters the antibody-antigen complex, it will activate the complement. That you can have a series of chemical reactions where these complement protein will actually make a pore. So we can make a pore here, a pore here, a pore here, a pore here, and a pore here. And essentially, the cell is losing its selective permeability. So things inside cell will spill out. Things out here will go in, which means the cell is lysing. So we can actually cause cell lysis by doing this activation of complement. So those are the three basic ways in which our antibodies help us: by neutralizing the pathogenic behavior, by enhancing our phagocytosis, and by allowing us to lyse cells where we have antibodies bound to it. But notice, this can only kill cells, so it's not going to kill viruses, because virus has no cell membrane. Yes?
I thought cell lysis was bad because it was going to release.
Right. Usually cell lysis is bad, but if you're destroying cancer cells,
Oh.
that's good, right?
Yeah.
So if you're destroying cancer cells, that's good. Or other cells, like bacteria. Bacteria is a cell. Okay, so that's good as well. Yeah, you don't want to lyse, although that does help. It does perform a role with that, which is it'll lyse the cardiac muscle cells. Maybe Kat donated her heart to Joan, and then his antibodies bound to it, and then we get complement reaction, and so essentially you're lysing those cardiac muscle cells, or what we usually refer to as the heart is rejecting that transplant, that graft. There's other ways in which we can reject that graft as well. Okay, so those are the three basic methods in which we use antibodies to fight infections. So the antibodies doesn't kill bacteria, does it? It neutralizes it. It allows your phagocytes to destroy it more readily, and allows a complement to. It's a complement that actually does the killing. Okay, so let's take a look at how our B lymphocytes produce antibodies. So this one's showing 3 different B lymphocytes. Each has a different receptor on the surface. So they recognize different foreign antigen. So imagine that you have the influenza virus, and this doesn't recognize any protein on the influenza virus. This does not, and this does not. And then perhaps you have a cold virus, a rhinovirus comes. This does not recognize, this does not recognize, this does not recognize. And then maybe you encounter staph. You have a staph infection. And that bacteria has an antigen that this will recognize. Okay? Once it recognizes it, it binds to it, you're going to activate it. So that that cell will first grow. Remember, it was a small lymphocyte before. Just nucleus, very little organelles. Now it grows, forms lots of endoplasmic reticulum, but it proliferates, so you have many of them now. They call this a clonal reaction, that you actually form a clone of many of these activated cells. And these activated cells are in 2 categories. They are what we call plasma cells or memory B cells. Okay. Plasma cells, those are the large lymphocytes now that have lots of rough endoplasmic reticulum, lots of mitochondria, and they are the ones that are actively making the antibody specific for that foreign antigen. But we do make some, we make too many actually, just a few memory B cells. These memory B cells has no role in our infection at this time. But these plasma cells, they're the one that's going to produce antibodies, and the antibody is going to neutralize that bacterial virus. It's going to enhance phagocytosis of that. And if it's a cell, you're going to enhance the complement reaction to destroy them. So this is what will be the active one that will fight. But it takes time for you to do this. And usually they say the average actually varies depending which cell, which lymphocyte that is. Some will take maybe 7 days to mount up a response. Others will take 14 days, others will take 21 days. They say the average is about 14 days. But it really depends on what is the antigen and which B lymphocyte you're exposed to. No drinking. Okay. This is responsible for our adaptive immunity, the memory B cell. So it has nothing to do during this initial infection. It's in your second time you're exposed to it, which is what we call the second challenge. So when these memory B cells, which were created from that original B lymphocyte, when it's exposed to that same antigen, say a year later, 5 years later, it will proliferate, make lots of plasma cells, makes lots of memory cells. Now, each of these plasma cells is much more efficient than the first plasma cell. It makes more antibodies than these did. And you also have many more plasma cells the second time around than this first time. So we're getting a much more robust reaction from a memory B cell. And one other thing which this does not show is it takes a shorter period of time. So if this takes the normal average 14 days to mount up enough antibodies to suppress the infection and stop the infection, this would take 24 hours, 1 day. So keep in mind that if this took you 14 days to mount up a response, that gave that infection, the bacterial virus, 14 days to exponentially grow in numbers. There's a constant divide. And so by the time you mount up enough response, that's a huge infection in your body, and that's where you get all these symptoms, whatever that infection is. Whereas over here, you only gave that bacterial virus 24 hours. Not much time to proliferate. And you mount up a much greater response than the first time, so you can actually wipe it out completely before any symptoms arise. This I got from another textbook. It's a very useful one.